marks aren't on the quiz, are they?
Oh,
Are the ones on the quiz?
no,
Okay.
I don't think so.
I didn't know we did.
I'm like 95% sure. It's gone.
Alright, I'm collecting 2 assignments from you guys, 83 and 84. That would be, 83 was the worksheet 1, worksheet 2, and 84 was the extra practice stuff. So most of you turned that into Google Classroom, but if you did not, and you want full points for it, then I need it in the basket before we get started here. Our quiz this morning is no calculator, so once you have your phones put up and your desk cleared off, I will bring it to you and let's start. Unfortunately, this quiz does not have point values, but you can assume each blank is roughly 1 point. so what I said about the point values is still true. Basically, all blanks are 1 point apiece. However, just to make sure that you're careful here, in question 5, there's a table and a graph. You do get 1 point for the table and 1 point for the graph. So make sure that you actually do those.
Push. Push.
Got it. Okay, let's move on. So you guys should have picked up 2 new handouts this morning. So we are moving on to logarithm stuff now. So fair warning, we did 1.9, which was just on inverse functions. Quick review, hopefully. We did, I guess, 2 days on section 3.1, which was exponential functions. But our next 3 sections, 3.2, 3.3, and 3.4, are all about logarithms. So some of the stuff we're going to talk about here in just a second will carry over for the next few weeks. So, of course, everything we do is fairly important, or we wouldn't spend class time on it. But again, this one you want to feel on top of. Otherwise, you'll feel like you're trying to play catch up for the next few weeks. Okay, so in section 3.2, the first part here, the shorter one, we're going to talk about graphing logarithmic functions and describing a little bit about the graph. So we did the same thing with exponential functions, but this one we're just going to do a whole page on. So first off, you need to know the relationship between this and this. 3 to the x, which we just reviewed a little bit about, and log base 3 to the x, these are inverses of each other. Likewise, log base 8 to the x and 8 to the x are inverses of each other as well. So make sure that you see that connection there. So we will ask you, what is the inverse of 5 to the x? And you should be able to quickly say that would be log base 5 to the x. Or what is the inverse of log base 2 to the x? And that would be 2 to the x. Exponential functions and logarithmic functions are inverses of each other, which is why we started this unit reviewing what it means to be an inverse function. So with this information, that's actually going to help us graph something like this. I want to know, what does log base 2 of x plus 3 look like as a graph? Well, the long way to do this, and this is fine at first because it reinforces your learning here, but we could graph 2 to the x. So 2 to the 0, 2 to the first, 2 squared, 2 to the third. He's an exponential growth. It's going to look like that. We can start off with 2 to the x. And the reason that's supposed to help you, and the reason why we do these lessons in this order, is if you understand these two are inverses of each other, and you remember that inverse just means you swap x and y, then you already know what log base 2 to the x looks like without me having to show it to you. So 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, 2, 4 becomes 4, 2, 3, 8 becomes 8, 3. You can switch x and y for as many of those points as you need to, and then you get his inverse, which happens to be log base 2 to the x. Now, not that this is really important right now, but remember, inverse functions always have this line of symmetry at y equals x. So it's good for you to visually see that as a little bit of confirmation that those are really inverses of each other. Okay, and then if I was trying to work up to this one, we're just going to apply our normal transformation rules. If I know what log base 2 to the x looks like, adding 3 directly next to x would shift it left 3, not right 3. And if I know some points, I just move them left 1, 2, 3, replot. Any of the points that look like they went through nice whole numbers, I would switch those around. And here is the function we are actually interested in. So we still need to use our transformation rules. We have to remember what inverse functions look like, and we have to be able to graph basic exponential functions. But if we can do that, then this is really just connecting those different pieces together and not so much something that's completely new. Now, of course, most of the time we ask you to work with something like this, we're not going to say, hey, start off with this, and then give you a little bit of push and get you to think of this, and then give you the final push to get you to where we want you to go to. A lot of times it's going to be like question 7. Graph this and or tell us its domain, what's its x-intercept, and what equation is this vertical asymptote. So when I look through all of this, I would say this looks like some transformations done to log base 3 to the x. And I have a good idea of what this looks like, but I'm more comfortable with this inverse 3 to the x. So me personally, I would graph 3 to the x, 3 to the 0, 3 to the first, 3 squared. He is exponential growth. Then I would take some of those points that I was sure about, switch x and y to get his inverse, which would be log base 3 to the x. I notice a line of symmetry at y equals x, so that is a good sign. And then I'm just going to worry about normal transformation stuff. So the order of these transformations does make a difference. So like I've mentioned in the past, if you imagine plugging in a number in for x, the first thing you would do is add 5 to it. So our first transformation is left 5. So I'm going to take these couple points that I'm sure about, move them left 5 and replot them. And notice there's this vertical asymptote at x equals 0. So if I shift the graph left 5, it's now at x equals -5. And this would be what log base 3 of x plus 5 looks like. Now, my graph's getting kind of busy here, so I'm afraid some of my previous work's going to kind of get in the way because I've still got 2 more transformations to go. So I would personally erase a couple of the previous steps that I don't need anymore. But I guess if you graph the first couple very, very lightly, then that's okay. Okay, the next transformation we would worry about is this negative, and that's going to flip it over the x-axis. So anything on the x-axis is going to stay on the x-axis, but this guy's going to flip down, and this guy's going to flip down. Should visually look like it has been flipped over the x-axis. And once I kind of verbally or visually confirm that, I don't need the step before that, so I'm going to take it away. And then finally, the last thing we would do if we plugged in a number for x is subtract 1. So that would be our last transformation. So I can move all of these points from earlier down 1. And if you have more than one graph on your coordinate plane over here, you need to make sure you label which one is your answer. This is I of x, so you can just put I of x by it. Don't have multiple graphs on there and not tell me which one you think is your answer. Okay, so then again, that's the real challenge there. So again, I started off with something that I knew would be helpful, 3 to the x. That's pretty easy to graph, and we just reviewed that. The top of this worksheet, I told you that this inverse was log base 3 to the x. So I took these points, switched x and y, and got these points. Then I did this transformation, graphed it, did this transformation, graphed it, and then finally the last transformation and graphed it. So you kind of have to walk yourself into it. Too hard to go straight to this. But now the domain looks like he goes as far left as -5 and forever to the right. He never quite reaches -5 though, so this has to be a parentheses. There is an x-intercept over here. That's at about, I don't know, -4 point something. Now, We actually care to be more specific than that, but we have to review a little bit of logarithms. But so once I show you how to do that algebraically, you should be able to give me an exact answer, not just a rounded answer. And then this is a vertical line that my graph can't cross. So that is the vertical asymptote. Because it's a vertical line, it should be x equals and not y equals. It's the line where x is always -5. So, if you're comfortable with exponential functions, if you're comfortable with inverse functions, if you're comfortable with your transformation rules, really the main thing you need out of this is just understanding how those couple things are connected. Okay, anything that jumps out at you about the graphing piece? Any of that I went over too fast? Okay, then let's move on to the second part, where it's not so much graphing, but what is a logarithmic function? When do we need them? When do we not need them? And start to dip our toes in some of the properties. Okay, so for the first couple up here, if I asked you to do this one, 2 to what power gives you 4? 2. Okay, 2 to what power gives you 5? You see how that's a little bit harder? So if it's a nice whole number, then sure, you can probably avoid logarithms. But when it's not a nice whole number, we have to have some kind of way to solve this and make it the only way to solve it is with logarithms. So let's come back to that in just a second. So one of the things you should be able to do with logarithms is go from exponential form to logarithmic form. So these four are what are called exponential form. Logarithmic form is going to have log in the answer. So to do this, you can just add log to your work as long as you switch the location of these two. So 3 squared equals 9 is the same thing as log base 3 of 9 equals 2. So I'm adding log to my work, adding it to the equation, but the 2 and the 9 have to switch locations. Okay, to do that here, I would need to switch B and C for me to make it logarithmic form. Over here, I would need to switch 16 and 2 to make it logarithmic form. And over here, notice this is the question up here. If I move this from exponential form to logarithmic form, it is now solved because we know what x equals. The exact answer to that would be log base 2 of 5. Now, while that may not be the most satisfactory answer, remember this is probably some decimal that goes on for a long time or forever, so we can't possibly write out those decimals for our whole life, so this is a way to keep up with the exact value. So sometimes simply switching from exponential form to logarithmic form is all you have to do to solve an equation. Now, we also will ask you to go the other direction. By the way, I have seen this stuff on the ACT quite a bit, switching from logarithmic to exponential, exponential to logarithmic. So it's basically like you're undoing the previous step. If you want to take log out of this so that it's no longer logarithmic form, you need to switch the x and the 2 back. And I guess if it's something like 3 squared, you can simplify. So to make log go away, you have to know which 2 things you can switch or have to switch. Now when there's numbers, usually the numbers have to be true. So 2 squared equals 4, that should make you feel pretty good about that one because that's a true statement. And then over here, if we switched them, this would be a to the b equals c. The exact opposite process. So really if you understand one process really well, then the other process should be pretty easy because you can just do what you think and then check it. If it's right, move on. If it's not right, then try something else. Okay, I'm guessing of the stuff that you guys did in Algebra 2 last year, you probably did these two. You remember this? But I don't, again, I know in Algebra 2, it's been several years since I taught it, but we used to do it in 2 weeks, which is just far too fast for you guys to understand this. But that's a good skill to have. It does help us with a couple different things. It does show up on the ACT, but most importantly, it does help us solve equations sometimes. So this equation y'all could not give me the answer to. That is the exact answer, and it's not that it was difficult or anything. We just have to know that process. Okay, sometimes the base is not going to be listed to you. So just like in algebra, when I say x, we all know I'm talking about 1x to the first. It's an understood 1x. We understand that the exponent is 1. We don't have to write that. With logarithms, the two big ones are natural log and then what's called the common log. And on your calculator, there's two buttons here, log and natural log. This is the common log. Then I'm about to show you what the base is. And then ln, that's for natural log. Those have an understood base of e and 10. So natural log means log base e. So if it makes you feel more comfortable, just rewrite the question. That's all that means. Natural log means log base e. Now normally you need to do something with that too, like switch the forms or something, but it's that same e, that number e that's in the PERT formula, and I showed you where that came from in your last notes. What about if there's not a base written? Do you guys remember what that is? Good. That is base 10. Base 10. The common log is referred to as base 10. So when you hit the log button on your calculator, it assumes you want base 10. If you hit the natural log button on your calculator, it's assuming you want base e. Those are the two most common ones. In calculus, we use natural log like 99% of the time. Regular logs don't come up too much. But. So if you don't remember that, make sure that you write yourself a note there. But we need to evaluate some logarithms without a calculator. Not that I've shown you how to do that anyway, but sometimes we can do that without a calculator. Sometimes we need a calculator to get the final answer. But let's think about how these are written and what we've already talked about on how to solve these. So I'm not going to go through the long process here every time, but for one time, let's go ahead and do it this way. If I just say, let me set this equal to x. So when I know what x equals, I'm finished with this question. Well, so far, the only thing I've taught you or told you about logarithms, really, other than graphing, is how to switch the forms. So this is logarithmic form because it has a log in it. But if I switched these two, it would be exponential form. And these are saying the same things. It's just that this one's a little bit easier for our head to wrap our head around. This is saying 7 to what power gives me 7? So the answer to that would be, so log base 7 of 7 is 1. Again, you can always just set it equal to x, switch the forms. If it's in logarithmic, switch it to exponential. If it's exponential, switch it to logarithmic. And then that often helps. But that's also kind of unnecessary. When I look at this, the way I read this to myself in my head is I'm saying 10 to what power gives me 100? What power on the base, not times what, that's an easy trap to fall in, but what power? 10 to what power gives me 100? And that would be 2. Now, because this is base 10, my calculator is set up to do that one just fine. So, of course, when we get to the quiz, you probably wouldn't get a calculator on something like this, but you can go ahead and check this one. It understood base 10. 10 squared is what gives you 100, so that's why the answer to that is 2. Okay, what is the base on this one? So this is saying 10 to what power gives you 10, so the answer would be, and that's all there is to it. 10 to what power gives you 1? 0. Anything to the 0 power gives you 1. 3 to what power gives you 27? Very good. Not 9. It's not 3 times what gives you 27. Even students who know what they're doing sometimes accidentally do that. It's 3 to what? 3 to what power gives you 27? Okay, what's the base on this one? So e to what power gives you e? Just 1. So like if you open up your textbook, there's probably a table of logarithmic properties, and it probably says to memorize some of these, and I guarantee you this one's in there. But why do you need to memorize that? You need to know what natural log is anyway. You need to know how to read a logarithm anyway. So this is just saying e to what power gives you e, so it's 1. This is saying e to what power gives you 1, and that would be, because anything to the 0 power is 1. And then what about this one? 2 to what power gives you 1/2? That's a little bit harder. Very good, -1. Remember, a negative exponent in the numerator, you can move it to the denominator, make it a positive exponent. Okay, there's also something called change of base formula, which you would often have a calculator for. To be honest with you, change of base is kind of getting outdated. However, there are some calculus things that we show proofs of that need to change a base. So if you don't know what change of base is, you get kind of lost on that. And then also, I think this still shows up on the ACT, and I know it does come up in college algebra still. They expect you to know what the change of base formula is. So the change of base formula is a way to say, well, my calculator only is set up to do base 10 and base e stuff, but what if I wanted to do base 3 or base 5? Well, you can do log base 10 of what you're taking the log of over log base 10 of the base, and that's the same thing. That is the change of base formula. Or if you'd rather, instead of doing base 10, you could do base e. So log base 3 of 7, since my calculator doesn't let me put in a base number, it doesn't let me change that, I could either type it in this way or this way. And you do need to know both, because we do ask that as multiple choice sometimes. Doesn't matter what your new base is, either both base 10 or both base e, but those are the two ways everyone's calculators are programmed that way. Okay, so this one, we could type in our calculator as log base 10 of 27 over log of 5, and, oh, I guess I should write the answer down, 1.771 over here. Now, before I move on though, shouldn't this kind of make sense as an answer? Like, I know you weren't going to come up with that decimal, but do you see why the answer to this has to be bigger than 1? Because 3 to the first is only 3, and why it has to be less than 2, because 3 squared would be 9. 7 somewhere between 3 and 9, so your answer is somewhere between 1 and 2. If it was like 8.9 or something, if it was super close, then this would be super close to 2, or very, very close. Okay, so you can do both base 10, or you can do both base e. Both of those are considered the change of base formula. Now, before I hit enter here, what kind of answer do you expect?
A little above 5. Or a 2, I mean.
Yeah, you see, you're thinking multiplication there. Because 5 squared would only be 25, and we want it to be a little bit more than that, right? So our answer is going to be a little bit bigger than 2. But if you need it to be 3 decimal accurate, you got to have a calculator. 2.048. And just to convince you, it doesn't matter if it's the common log or the natural log, you just need to be consistent. You also have to make sure you put the correct one in the numerator and the correct one in the denominator. So I'm guessing you guys saw change of base in Algebra 2? Okay. Did you guys remember the formula though? No? Okay. Okay, so one way to solve equations is just switching the forms. So sometimes we can get away with just taking it from logarithmic form, switching it to exponential form, or if it's in logarithmic form, we can switch it to exponential form. Sometimes that is enough to solve the equations, and that is a good thing to start off with. But there is this special property. This is really what makes logarithms super useful. If you're trying to solve for something in the variable like this, if it's an exponent on something that you're taking the log of, this can come down out front like so. The exponent on the thing that you're taking the log of can come down out front, and then it becomes multiplication. So how that's helpful to us is we can solve something like this that the other algebra skills you have just don't help you with. You can't solve for a variable that's stuck in the exponent without logarithms, unless the question has been rigged to be super nice. So on a question like this, I don't know why we got two of them, but what we could do is we could take the log of both sides or the natural log of both sides. It doesn't matter, as long as you do it to both sides, it stays balanced. And then because of this property, now this x plus 2 is an exponent on something I'm taking the log of. So this x plus 2 can come down out front, and that is unique to algebra. That's the only way that you get something out of the exponent so that you can just finish solving for it. Okay, and then so the work looks a little bit weird because we've got natural logs all over the place, and now it's going to solve the same way you solve stuff all the time. Distributing this, anything without an x, I'll move over to the other side. So undo plus with minus, and then undo times with divide. Crazy looking answer that you would never guess with just trial and error. But taking the log of both sides so that this property can be applied, so we can get that exponent, that variable out of the exponent, and then we can use our normal solving techniques. Distribute, undo add, undo times. So if I go ahead and take just a second here just to convince you, I'm going to ask my calculator to store this. Okay, and when I do that, it also changes it to a decimal for me. So if I want to know approximately what my answer is equal to. But I use this store button down here. I know I've shown this to you guys a few times this year, but I stored it in for x. And then what I can do is I can type in that original problem, 4 to the x plus 2. And 4 to the power of x plus 2 is supposed to equal what? If this is really our answer, then it should be 6. And so we must have a mistake somewhere.
You wrote x plus 3 instead of x plus 2. Sounds like when you put it in time.
Okay. So sloppy handwriting. This should be a 2. This should be a 2. This should be a 2. So I didn't do that on purpose, by the way. But that's exactly where that could be helpful, even if you feel comfortable with what you're doing. This should be a 2. So looks like our final answer was exactly 1 bigger. It's interesting. And then So if that's really what x equals, then 4 to the power of x plus 2 should be 6. So even though my answer looks very strange and it looks like there's no way that could be the answer to the problem, it makes that original equation true. So now I'm 100% confident in it. I was pretty confident on it with the 3 too, but I just copied the question down wrong. Okay, so this one, again, this is what makes logarithms useful. This property, we're going to use that a lot. Anytime you have an exponent on something you're taking the log of, consider bringing that down. If you don't have logarithms in the question, you're welcome to introduce them. Just make sure that you take the logarithm of both sides so that it stays balanced. And if you don't want to do natural logs, you can do common logs as well. If I did log base 10 here, log base 10 here, my answers would have log base 10, log base 10, and log base 10, and it would still work. Okay, another property, this one doesn't show up too much in here, but it does show up a lot in calculus. In fact, I think it's showing up for the first time today, even. It's in that lesson, but I don't know if we get any questions like this today. But there is this property in calculus that says if you have a number and his exponent is log and the base is the same number of something, all of that just comes out to be the something. Now, when we get closer to the test and we have a little bit more logarithm stuff under our belt, I can show you why that works that way. But temporarily, I just need you to be able to get that from pattern recognition. So, why we do this, or why this is needed in calculus, this is a good review for me in case it comes up today, is sometimes this is a really unusual algebra set that you've never done. It's called exponentiating. I would really like to make this left side of my equation be the exponent of e, which is okay as long as I make the right side be the exponent of e. That's called exponentiating. The reason why I wanted to do that is because now this is this property. This is e to the log base e of y. So as long as these two numbers are the same, it's just going to simplify to what you're taking the log of. All of that just becomes y because of this property. And then over here, sometimes we need to do more stuff with that. But it's kind of a way to, if you're trying to solve for y and y is stuck inside that natural log, you can't just undo a natural log with division. This isn't natural log times y, it's natural log of y. So to be truthful, this property is probably not going to come up in anything that we do, but we will expect you to know this property and be able to answer it. So maybe just write out a couple more examples, like if it was log base 3, or 3 to the log base 3 of 5, it just equals 5. If it was 7 to the log base 7 of 25, it's going to be 25. As long as those numbers are the same and it fits that format, it will all simplify to what you're taking the log of. Okay. Evaluate using log properties. So if we use some exponent rules, this is where it kind of helps to do 3.1 first. So 99 times out of 100, if you have a negative exponent, you move it to the opposite side to make it have a positive exponent. But on this question, I'm moving this from the denominator to the numerator, so I'm changing its sign on its exponent. And the reason why I would do that is because now this is an exponent on something I'm taking the log of, so I can freely bring that down. And what is the log of 10 equal to?
1.
1, because this is saying 10 to what power gives you 10. So the whole answer is -5. Now, we will talk about expanding and condensing logarithms, which I think you probably also did in Algebra 2. But that doesn't come up for a couple, or till 3.3. But you'll have some options on how to do that after we review that. Okay, if I do that over here, I can bring e to the positive 7 out of the denominator, move it to the numerator, as long as I change the sign. Again, most of the time in mathematics we want to move it to a positive exponent, but in this case we want a negative exponent. Because now we've got an exponent on something that we're taking the log of, so it can be brought down out front. And the natural log of e is something we can evaluate in our head, because it's saying e to what power gives you e. So your answer comes from negative 7 times 1. So using exponent rules. Now, if there's more than one term, the whole thing becomes negative. So if I move all of this up, that's not correct. It's not that you're just making the x negative, you're making the -1 negative as well. If you move it from one side of the fraction to the other, all of it has to switch. Then all of this is an exponent on something I'm taking the log of. It can come down out front. The log of 10 is going to be 1 still, for the same reason it was up here. And so we're left with this as an answer. Your answers don't have to be numerical. If there's an x in there, then you might have an x in your answer. We are not solving equations yet. Okay, so if I rewrite this one, this would be the same thing as the natural log of e to what power? You said -3x, and then minus 2. Okay, the whole thing becomes negative. Then this is an exponent on something that you're taking the log of, so you can bring it down out front. Natural log of e is still 1. You're going to get sick of me saying some of these, but this is because e to the first gives you e. So this times 1 just gives you this. So sometimes on some of the harder questions, we have to use a little bit of exponent rules before we can use one of those properties. Okay, to graph what a logarithmic graph looks like, we talked about this a little bit on the other page, but I know that this guy is inverses with 3 to the x. So if you know what 3 to the x looks like, you could take those points, switch x and y, and then you should pretty quickly know what log base 3 to the x looks like. What would the inverse of this one be? What's the inverse of log base 5 to the x? Okay, and then just like we looked at in our 3.1 notes, the graph of 3 to the x, the graph of 5 to the x, the graph of e to the x, they all basically look the same. Now how quickly they hug the x-axis and how quickly they rise vary just a tiny bit, but that means that their inverses, log base 3 to the x, log base 5 to the x, log base e to the x, all of those graphs basically look the same as well. They all have an x-intercept of 1, they all have a domain of 0 to infinity, they all have a vertical asymptote at x equals 0. The general shape of all logarithmic graphs, if there's no transformations, basically look the same. Just like the exponential functions, whether it's 3 to the x, 5 to the x, or e to the x, all basically look the same too. Okay, one of the harder things for students is trying to find this vertical asymptote sometimes. So let's look at a few examples here, and the last couple are the ones that are the trickiest, I guess. But if we have a general idea of what log base 3 to the x looks like, his vertical asymptote is right here. The vertical line, which makes it x equals, that the graph can approach but not cross. Now, if you shift your graph left 4, then that vertical asymptote is also being shifted left 4. whole graph moves that way. So was that x equals 0? You shift your graph left 4, now it's at x equals -4. But these two are the ones that often give students issues. Alright, well first off, this would look like log base 3 to the x. Try not to do too much at once. What happens when we put the negative directly on the x? Does that flip it over the x-axis or the y-axis? That's over the y. If you want it over x, you got to multiply the whole function by that, not just x. So this looks like this. Now here's the part that I think you guys just have not seen before. Okay, when we add 4 to x, I've drilled into you many times this year that goes left 4, correct? Well, if you flip over the y-axis, those rules actually switch, because what's really happening is the negative isn't just going to the x, it's also going to a -4. So this is actually right 4. The rules for left and right transformations switch. 1, 2, 3, 4. The rules for left and right switch if you're reflecting across the y-axis, because the negative, even though it doesn't look like it, is going to the x and the 4. So if this guy, if the original function had a vertical asymptote at x equals 0, flipping it over the y-axis kept it at x equals 0, but then if I went right 4, now he's at x equals 4. And it's an asymptote, so I really should do a dashed line instead. Okay, so one more to try to hone in on that. Here's what the natural log of x looks like, because all logarithmic graphs basically look the same. The x here is going to flip it over the y-axis, which is going to make it look like this. And then +7 means left 7 unless you're also flipping it over the y-axis. You should probably write it out like this on your paper. The negative is really going to both of these, so this is actually right 7. So if his vertical asymptote was at x equals 0 and you shift it right 7, it's now at x equals 7. So it's not a hard concept, but again, I think in Algebra 2 they just kind of avoid you having to deal with that. So you might want to write yourself a note about that. At least in the past we've had a question similar to those. And that's how I would do it. Sketch the logarithmic graph, flip it over the y-axis if that's part of the transformation, and then shift it left to right, and be careful that you're going opposite of what you normally think if you're flipping over the y-axis. Okay, and then last part, so very good timing for this today. You need to know that there are some things called extraneous solutions. So the quickest way to do this is to make sure that you never take the log, regardless of base, of any negative number, we need to write this in, or 0. So just to show you why this doesn't work, before I work a question like this, or a basic one like this. If I ask you 3 to what power gives you 0, you see how you can't answer that? You're tempted to say 1. 3 to the 0 is 1, but there's no power of 3 that ever gives you 0. If you think about the graph 3 to the x, he never equals 0. He never gets down to that. That's why you can't take the log of 0. Basically the same reason you can't take the log of a negative number. Now you can have a negative answer. We had a negative answer up on page 2, I think. But there's no power of 3 that gives you a negative number. Same thing. If you think about 3 to the x graphed, he never equals -1. So the thing that you need to instill in your head to help you check that, because you're not going to want to think about that visually all the time, you can never take the log of negative number or the log of 0, regardless of the base. Now, in section 3.4, the last thing that we do with logarithms, we spend a lot of time with solving equations, but in this section we just give you some kind of easy ones to help you get started. So what I mean by easier is this one's been rigged a little bit for you. This is log base 3 of some stuff, this is log base 3 of some stuff, so if you want these to be equal, you just need the stuff to be equal. You need the inside parts to be equal. So you can set those to equal to each other, subtract an x from both sides, subtract a 5 from both sides, circle your answer, but then you need to be careful. Can I have a negative answer? I can have a negative answer. I can't take the log of a negative number. So if I was to plug it in up here, it would be log base 3 of 3 equals log base 3 of 3. These are the same thing, right? And I'm not taking the log of 0, I'm not taking the log of a negative. You can have a negative answer, you just can't take the log of a negative number. I know it sounds similar, but not quite the same. Over here, this is log base 3, this is log base 3, so those are already equal. So we just need to make sure that the insides are equal. And in this one, just going to require a little bit more work because it is a quadratic. To solve a quadratic, you want it all on one side set equal to 0. Solving a quadratic often gives you 2 answers. But these might be extraneous. This solves this, which solves this, which solves this, which we wrote this way out of convenience, but one of these answers doesn't work. And if you had to guess without looking at it, I think you would say it's a -1. But again, you can have a negative answer, you just can't take the log of a negative number. If I plug in -1 up here, I would get 1 minus 3, which would be -2, and +2. Well, that doesn't work anyway. Oh, yeah. Because you can't do this. You can't take the log of a negative. So this is extraneous. But also, if I plugged in 3, 9 minus 3 would be 6. Plug in 6 here. Can't take the log of a negative. Both of those were extraneous. So this had no solutions. So again, really what you need to do for at the end of a question is just train yourself to make sure that none of your answers plugged back in give you the log of 0 or the log of a negative. Bless you. Okay, that's all I've got for you guys today. We've got just about 4 minutes left. I do think it would be helpful if you spend just 5 minutes kind of scanning through that before next class, since we're going to be using some of it. And of course I will verbalize it and stuff again, but the sooner you become accustomed to those things, the easier it will go.
So you got
Maybe.
just sharing.
I can ask him if it's larger, but I don't know, he hasn't even said anything. He didn't say it needs to go out at last class.
Yeah, so that's why I'm kind of thinking, how long is class?
Yeah.
Yeah, I know. I thought that she would dance.